This stimulated emission is the key mechanism behind how a laser is working. So of course we would want to have a lot of stimulated emission to make our laser work, because that means we're going to get more photons out of our laser. So how do we do that? There are two things that we need to do in order to make sure that we can enhance this stimulated emission and therefore make a more powerful or more efficient laser out of this mechanism. The first thing that we need is something called population inversion. And the second thing that we need is something called a resonant cavity. So in this video, we are going to look at population inversion and what it is. Population inversion means that we have more electrons at a higher energy level as compared to a lower energy level. So when we talked about our two energy levels to make in our previous examples, for stimulated emission to occur, I need to have electrons at this higher energy level that are ready to fall down to energy level 1 in the presence of a photon. Okay, so or this is actually energy level 2 is actually a band of energies. But anyway, we need this kind of situation to occur to have population inversion. And this is not something that naturally occurs, because as we for all systems, the energy or the system wants to get to its lowest energy level state. So this is not the lowest energy level state. It's not something that will naturally happen. So we need to engineer a way to make population inversion occur. And we can do this in a p-n junction. So how are we going to make population inversion happen just using a p-n junction? Well, let's start with a degenerately doped p-n junction. Okay, so I'm going to draw the band diagram in thermal equilibrium first. So I'll draw the Fermi level as a constant because we're in thermal equilibrium. On the p side of the junction, it's degenerately doped, so the Fermi level should be in the valence band. On the n side of the junction, it's degenerately doped, so the Fermi level should be in the conduction band. And then we have the bands bending through the depletion region. Okay, so this by itself, this degenerately doped p-n junction by itself, does not give us population inversion. But now let's look at the band diagram when we forward bias it. Okay, so we're going to forward bias our junction. That means we're going to offset the Fermi levels on either side of the junction such that the potential barrier in the valence band and conduction band becomes lower. Okay, so let me draw the p side first. I'm applying a forward bias, offsetting the Fermi levels. Okay, here's the Fermi level on the n-type side. This is the this offset is due to the applied forward bias voltage. And now what we can see from this diagram is if we look at this part of the depletion region, that I just outline with these dashed vertical lines. I have a population of electrons here in the conduction band. I know that there has to be some electrons there because that's below the Fermi level. And I have some empty states available in the valence band. So, and I know that there has to be some empty states there because that's above the Fermi level. So I have more electrons at a higher energy level, the conduction band, than there is at a lower energy level, the valence band. So more electrons at a higher energy level, empty states at a lower energy level. This is exactly the definition of population inversion. So by forward biasing this degenerately doped p-n junction, we are able to get population inversion. And now if I have a photon coming in, that can trigger a transition of the electrons in the conduction band to the valence band. This is photon 1. Photon 1 is not absorbed, it goes through, but I will create photon 2 with the same phase and the same frequency as photon 1. So I'm getting stimulated emission in this p-n junction structure because we were able to create population inversion.